Let vector v sub 1 be defined as -2, 4, 2, let vector v sub 2 be 1, 0, 1, and let vector v sub 3 be 4, -4, 0. Use row reduction to determine if the set v sub 1, v sub 2, v sub 3 is linearly independent. If possible, find a linear dependence relation amongst the vectors v sub 1, v sub 2, and v sub 3. So, to get us started, what is the goal here? So in order to determine if the set of vectors is linearly independent, we want to determine if a non-trivial solution exists to the vector equation. So to the equation, specifically here, x sub 1 times vector v sub 1 plus x sub 2 times vector v sub 2 plus x sub 3 times vector v sub 3 is equal to the 0 vector. So how are we going to determine if a non-trivial solution exists? We're going to need to row reduce the equivalent augmented matrix. So we want to row reduce the augmented matrix, v sub 1, v sub 2, v sub 3, and we're augmenting this with the 0 vector. Again, keep in mind, this is the same thing as simply thinking about your coefficient matrix, v sub 1, v sub 2, v sub 3. And we're going to row reduce this to that echelon form to see what is going on. So here we go. We have our augmented matrix. V sub 1 is -2, 4, 2. Our second column vector is v sub 2, 1, 0, 1. And last but not least, we have v sub 3, which is 4, -4, 0. Alrighty, so I would like to try to avoid fractions if we can. So what I'm going to do here to row reduce this is to take 1/4 of the second row, and I'll interchange that with the first row. And so this leaves us with the equivalent matrix, 1, 0, -1, -2, 1, 4, 2, 1, 0. Beautiful. So now I'm taking my first pivot position, and I want to use this to eliminate the entries below it. So we'll need 2 steps. Step 1 is to multiply the first row by 2 and add this to this second row to attain the new and reduced second row. And then we'll go ahead and we'll take -2 times the first row, and we'll add that to the third row to attain the new and reduced third row. So here we go. This leaves us with the augmented matrix. So our first row is still 1, 0, -1. The second row, we have 2 minus 2 gives us 0. We have 0 plus 1 leaves us with 1. And last but not least, we have -2 plus 4 is 2. Beautiful. Now, for the third row, we have -2 plus 2, which gives us 0. We have 0 plus 1, which leaves us with 1. And last but not least, we'll have +2 plus 0, which leaves us with 2. And would you look at this? Our first column is all set. Moving on to the second pivot. To eliminate the entry below it, we simply need to do -1 times the second row plus the third row to attain the new and reduced third row. And because the second and third row are the same, that entire third row is eliminated. So we're left with the equivalent matrix 1, 0, -1, 0, 1, 2, 0, 0, 0. Oh, and look at this. Not only do we have echelon form, we have row-reduced echelon form. So we know that at least one solution exists. The system is consistent. Now, because the entire third row is zeros, we don't have a pivot in the third row, and this is indicating to us that x sub 3 is free. It's a free variable. So therefore, if x sub 3 is free, this means that a non-trivial solution exists. So therefore, a non-trivial solution exists. And the set of vectors, v sub 1, v sub 2, v sub 3, are linearly dependent. So there we go. That's the first part of our solution. Again, because x sub 3 is a free variable, a non-trivial solution exists to our vector equation, and the set of vectors is linearly dependent. So since these vectors are linearly dependent, we can now go ahead and find a linear dependence relation amongst the vectors. So part 2 is to find a linear dependence relation amongst the vectors v sub 1, v sub 2, v sub 3. Now keep in mind here that infinitely many possibilities are going to exist. So we'll just look at one or two. So we're taking this matrix in its row-reduced echelon form, and let's convert this back to its equation form. So what is this telling us? Well, the first row tells us that x sub 1 is equal to x sub 3, our free variable. The second row is telling us that x sub 2 is equal to negative 2 times x sub 3. And of course, we know that x sub 3 is free. So we can see the relationship amongst these three vectors. And of course, this is such that x sub 3 is a real number. It's any scalar our little hearts desire. So we're going to use this to help us find a linear dependence relationship. Now, to do this, to find a linear dependence relation, we simply need to choose any value for x sub 3, our free variable. So let's look at, we'll do a nice easy case. Let's let x sub 3 be 1. So what does this mean x sub 1 and x sub 2 are? Well, x sub 1 equals x sub 3, so x sub 1 will be 1. X sub 2 is equal to negative 2 times x sub 3, so we have negative 2 times 1, which is negative 2. And we already know that x sub 3 is 1, so therefore one possible linear dependence relation is going to be defined as 1 times vector v sub 1 minus 2 times vector v sub 2 plus 1 times vector v sub 3 equals the 0 vector. So here is one of infinitely many possible linear dependence relations. We can even make a little love note here to ourselves that this is giving us one particular solution to the system. So this particular solution that we have defined for vector x, our particular solution here is 1, negative 2, 1. Beautiful. And let's do one more for good luck. Pick your favorite number. So I'm going to go ahead and I'm going to let x sub 3 be 17. So, since x sub 1 is equal to x sub 3, we know that x sub 1 will be 17. Since x sub 2 is equal to negative 2 times x sub 3, x sub 2 will be negative 2 times 17, which gives us minus 34. And again, we already know what x sub 3 is because we chose it. So therefore, another linear dependence relation amongst these vectors is defined as 17 times vector v sub 1 minus 34 times vector v sub 2 plus 17 times vector v sub 3 is equal to the 0 vector. So here is another possible linear dependence or relation amongst these three vectors. So we'll make a little love note here to ourselves that these are just two of infinitely many possible linear dependence relations. And it's linear dependence relations among these three vectors, v sub 1, v sub 2, and v sub 3. And one final love note, looking at this second linear dependence relation that we have defined, we can see that the particular solution to the corresponding homogeneous equation, in this case, vector x is defined as 17, negative 34, 17, which is a scalar multiple of the particular solution we found in case 1.